Welcome, Calc students, to our video notes lesson on the chain rule, or at least the first part of the chain rule. So you should have already completed the first part of this outline by watching the delightful video by Professor Berger, especially the part with the bifurcating onion. Don't think I've ever heard that word used in any other context. But anyway, hopefully it gave you a good visual as to what the chain rule actually is. It's peeling apart the different layers of a function and taking the derivatives of them separately. So here is the actual formula for the chain rule. And basically what it tells us to do is to first take the derivative of the outer layer, which in this case, in this generalized formula is f, but you keep the inner function plugged in. Like you keep g of x there intact. This is sort of like the inside layer, or as Professor Berger refers to it as the blop. You keep that there, and then you take its derivative and multiply that to the outside of f prime. So you take the derivative of the outer function, keep the inside function inside, and then take the derivative of the inside function and multiply it to the outside. That is generally what the chain rule says to do. So let's do example 1 together. And in example 1, we have the function quantity 2x minus 8 raised to the 4th power. And we're finding the derivative of that function. So what I want you to notice is that we basically have an outside layer of taking something and raising it to the power of 4. We can think of that something as our blop. And our blop is, in formal terms, is our inside function, our g of x. So our g of x in this case is 2x minus 8. That's our blop in this case. So first, I'm going to take the derivative of the outer layer. The outer layer is the power of 4. So I'm going to first use the power rule. And I'm going to take 4 times the g of x function, which is 2x minus 8, that blop, raised to the power of 3. So first I used the power rule for the outside function that was blop to the power of 4. And I got 4 times blop to the power of 3. So this is the f prime of g of x part. So I've taken the derivative of the outer function and I've kept the inside function inside. Then I take the derivative of my inside function, so the derivative of g is just 2 because it was just a linear function. Derivative is the slope is 2. So I'm going to multiply that to the outside of my f prime equation. So this part is the f prime times g, and this part is the g prime. So I then simplify from there. I can go ahead and multiply the 4 and the 2. So that would be 8 times the quantity 2x minus 8 to the power of 3. And there is my derivative of f. So now we're going to take a look at maybe some more complicated functions. Now I have a trigonometric function, tangent. And whenever you see the little power of 2 written in between, like tan squared of x, first of all, we would read that as tan squared of x. That's how you would say that out loud. And what that means is we take the tangent of x and then square the result. So I'm squaring the tangent function. So what that means is that the tangent function on the inside, that's like my blop. So I can think of y as blop squared. And the inside function is tangent. So we're going to multiply by the derivative of tangent after I take the derivative of the first layer. So the first layer is the squaring layer. So the first layer is blop squared. So I'm going to take the derivative of that. Derivative of the first layer would be 2 times blop to the first power. So that's what I'll start with. So y prime, right, derivative of y, would equal 2, because that's the outer layer, times tangent, that's my inner blop, right? This right here is my blop. and then all of that to the first power. So right there, that's my f prime of g of x. That's my power rule that was done leaving g of x plugged inside. Then what I need to do is multiply that by the derivative of the blob. So that would be the derivative of that inside function, the derivative of tangent. So we now know that that is equal to secant squared. So I'm going to multiply by the derivative of tangent, which would be secant squared of x. So here is my f prime of g, and here is my g prime of x. And so that's essentially what the chain rule requires us to do when taking the derivative of a composite function, one function plugged inside another. I have to figure out what the inside and outside layers are. So I noticed my outer layer was the power of 2. So I take the derivative of the outer layer while keeping my inside function plugged in. And then outside of that, I multiply by the derivative of that inside function. We call it g of x. And it's a product of two different things. And then I just simplify at the end, although not much simplifying I can do here, but I don't need the parentheses. I can think of this as 2 times tangent times secant squared. And you can leave it that way. Or if you prefer to have things in terms of sine and cosine, we could remember that tangent is sine over cosine, and secant is 1 over cosine. And since it's secant squared, this would be cosine squared. So you could also think of this derivative as 2 times sine of x divided by cosine to the third. Either way is fine. And so that would be my derivative of y in example 2. So in example 3 here, we have a rational function, and we could use the quotient rule to find the derivative of this, which we learned in our previous section, 2.3. So in this section, we're going to show you another option where we could use the chain rule and the power rule instead. But first, it would require us to rewrite the equation as 2 times the quantity x minus 3 to the power of negative 1, because that's what it means to divide by something, is you're raising it to the negative 1 power. And in this case, it was being multiplied to 2. So this is my g of x function. And I want you to think of this inside part, right, the x minus 3, as just like a blob, right? So the outer layer to this function is basically 2 times something to the negative 1 power. So that's the outer layer, so I would take the derivative of that first. So g prime of x is equal to negative 2 times the blob, if you will, to the, and then remember, when you subtract 1 from negative 1, you get negative 2. So at this point is when you would plug in your inner function inside here. So when you take the derivative of the outer layer, the inside function stays put. Like you don't do anything with it. You don't take its derivative yet. You just plug it inside the derivative of your outer function. And then here's where we multiply by the derivative of that inside part, the derivative of x minus 3. But the derivative of x minus 3 is just 1. So I would just be multiplying by 1. And that means that my derivative in this example is just equal to negative 2 times the quantity x minus 3 to the power of negative 2. Or you could write that as negative 2 divided by the quantity x minus 3 squared. So actually, put a little star by this one. This would probably be an easier method for finding the derivative of this function than the quotient rule would be. Because we don't have to really do much simplifying. We just take the power rule and then we're pretty much done. So in example 4, you can see we're being asked to take the derivative of a square root function. So first I would want you to recognize that a square root function is really a power function. So I would rewrite it as x squared plus 4x plus 1, all being raised to the power of 1/2. So a 1/2 power is has the same meaning or value as a square root. So then I would want you to notice that this is basically just some blob to the power of 1/2. So my outer function in this case, outer layer, is the power of 1/2. So when I first begin to take the derivative of this, I will start with a power rule. So I'll do 1/2 times the blob, which was x squared plus 4x plus 1. And then when I take a power power rule with a 1/2 power, don't forget when you subtract 1, the result is negative. So I have 1/2 times the BLOP to the power of the negative 1/2. So far, that is taking care of the outer layer. And now I move to the inside, this part here, and I have to now multiply by the derivative of that inside part. So that I can take the derivative of using, again, power rule, so that would be 2x, and then constant multiple rule, which would be 4. So now that looks like this. 1/2 times x squared plus 4x plus 1 to the negative 1/2 times the quantity of 2x plus 4. So what I'm going to do is simplify this part a little bit, multiply it to the 1/2. So that'll just turn into x plus 2 when I multiply those together. And then this is being raised to a negative power, which actually indicates that it needs to go into the denominator. It means I'm dividing by that square root. So I will do that. I'll put that down in the denominator. And you can either put it back into the square root, or you could just leave it to the power of 1/2 as long as it was in the denominator. And there is my derivative for p of x. Now, last but not least, we're going to end with some transcendental functions, an exponential and a trig, where they are the outside layer. So notice in example 5, part A, I have e being raised to the power of negative 6x. So in this case, the inside, if you will, is the exponent. So the inside of an exponential function is the exponent. So this would be where my BLOP would be hiding, or not so much hiding, it's right there in our face. So I need to think of this function as e to some BLOP. And so the derivative of e to any power is just e to that power. So I start by just repeating the same thing. So I start by e to the negative 6x. But then I have to go back to what that inside function was, what my BLOP was. So it was negative 6x. And I have to multiply the derivative of that to the outside of e to the power. So the derivative of negative 6x is just negative 6. So in my derivative here, I'd have e to the power of negative 6x times the derivative of negative 6x, which is negative 6. And the way that this looks best, like the way that you'll see it written, is with the coefficient in front. So we would write this as negative 6 times e to the negative 6x. There's my derivative of part A. Now, in my derivative for part B, we'll do that down here. So I have my equation. G of x is equal to sine of pi times x. So the inside of this function, my BLOP, is the pi x. That's the inside. And my outer layer is the sine. So the outer layer is basically sine of BLOP. So when I'm taking the derivative of that, so the derivative of g, I would have to start by the derivative of sine. So the derivative of sine would be cosine. But at first, I just leave the BLOP, if you will, this inside function, plugged in. So it starts off this way. Cosine of pi x. So that's the outer layer. Then I need to revisit this inside layer, right, this pi x, and I need to multiply by its derivative. So then I go to the inside. First I take the derivative of the outer layer, which brought me to cosine. I keep the inside plugged in and don't do anything with it yet. Then on the outside, I multiply by its derivative, which in this case is just the constant, right, the coefficient in front of x. So my final derivative for this, and again, we like to put the coefficients in front, would be pi times the cosine of pi x. There is my derivative of sine of pi x. So this was just kind of our introduction to the chain rule. These are just some basic examples. We're going to practice some of these in class, and in our next video, we'll visit some harder examples. See you then.